All right, so today we're going to talk a little bit more about the energy of life. We briefly introduced this concept of energy and the requirement of energy when we characterized our characteristics of living things. And we said that all living things requires energy in order to fuel life processes, right? So energy and metabolism, we're clear that all living things require energy to carry out life processes. The cells need energy to grow, reproduce, and to be able to maintain themselves, right? We talked about that concept of homeostasis, and that is the organism's inherent system in place to keep a nice and balanced internal state, right? We need energy to do that. So cells can obtain energy in many different forms, but that energy must be converted into usable forms, right? So we've talked about cellular respiration already and how we obtain energy from the foods that we eat, right? So let's talk a little bit more about this energy and metabolism, right? So cells have mechanisms in place that convert energy from one form to another, right? So we're going to take a look now on some basic principles of how cells capture, transfer, store, and use energy. All right. How do cells capture, transfer, store, and utilize energy? Okay. So what is energy? Right? If you had to define energy, how would you define it? What is energy? What is energy?
Isn't it like something that can be created or destroyed?
You said it can or cannot?
Cannot.
Cannot, right, right. So it cannot. We're going to take a look at that. In fact, that defines one of our laws, right? We understand laws and theories in science. Thank you so much for that. All right, so the definition of energy can be defined as the capacity to do work, okay? It is any change in the state or motion of matter, right? So we said that matter was anything that has mass and takes up space, right? So anytime there's a change in the state or the motion of that matter, we have energy, all right? So we usually express our energies in a unit of work that we call the kilojoule. Write that down, right? Kilojoules, all right? Energy can also be expressed as a unit of heat, all right? Heat energy is the kilocalorie, right? So one of the things that you saw back when we talked a little bit about energy, on that energy pyramid, we saw that energy is transferred from one trophic level to the next, but we also showed you that energy is lost in the form of heat, right? So heat energy is when we have this thermal energy that flows from an object, right? Energy can be released as heat, all right? So what are some types of energy? I know you guys kind of remember, even in your high school class, you learned about some types of energy. Can anybody recall a type of energy?
Potential. Kinetic.
Potential energy. What's another one?
Kinetic.
Kinetic energy. Yes, absolutely. So we have some different types of energy, right? Organisms can convert this energy into either kinetic energy or potential energy. All right. Kinetic energy is defined as energy of motion. Write that down. Kinetic energy is used when work is being performed. All right. We use kinetic energy when we are doing work, right? Potential energy is the capacity to do work, right? So this potential energy is there when needed. So it is the energy that is stored in an object, all right? Chemical energy is stored in these chemical bonds, right? So in the foods that we eat, that's the energy that we're trying to harness, right? When our bodies undergo cellular respiration, that chemical energy, all right? So we have two types of energy here. Kinetic energy, which is energy of motion. We're using kinetic energy whenever we're doing work, all right? We are expending this kinetic energy. And then we have potential energy, which is the capacity or the capability to do work. So this is the energy that is stored in an object, and it is used when an object begins to become work. We have something in the chat. Yes. Okay. All right. So thermodynamics. Thermodynamics is a branch of science that studies energy and its transformations. All right. So scientists do study this in terms of a system. Right? When we study energy, we're studying it in terms of a system. All right. This is the object that is being studied. Everything around that object is its surrounding. All right. So I want you to jot these terms down right now. We're talking about a system, which is the actual object. And then everything around that object is its surrounding. All right. So we can define a system, right, as either a closed system or an open system, right? We, for example, are an open system, right? This is the object that's being studied. Organisms are an example of a system, all right? Closed systems, by definition, do not exchange energy with its surroundings, with its environment, all right? Open systems can exchange energy within the surrounding, all right? So we're talking about thermodynamics as the study of energy and its various transformations, all right? So we're studying this energy as it relates to a system, right? Systems can either be open or closed, right? Closed systems do not exchange energy with its surrounding or its environment, while open systems can, okay? Make sure you jot that down. All right. So biological systems. We are biological systems. We are an example of an open system, right? We are very clear that we, organisms, exchange energy with its environment. Write that down. All biological systems are open, okay? Boundaries are set to allow for this exchange of energy for the purpose of growth and change. So when we're eating and consuming our foods and so forth, there's certainly going to be this exchange happening. All right. Boundaries are set to allow energy exchange for the purpose of growth and evolution, if you will. Okay. Change. All right. Biological systems are open systems. So this is a schematic just for those of us that are visual. Whatever object we're studying here is the system. Okay. This is our system right here in yellow, right? Everything else around it is the surrounding. So we use the system and surrounding. I would like for you to be able to describe the relationship with energy in terms of a system and its surroundings. So there are boundaries, right? I mentioned that there are boundaries in place that impact this exchange of energy. All right. So we have a system, we have the surroundings, and then we have this boundary that's in place. All right. So someone responded to me earlier and said that energy cannot be created or destroyed, right? Let's look at that. Yes, the energy in our universe. One of the first laws of thermodynamics tells us, yes, that energy cannot be created or destroyed, right? It can only be transferred or converted to a different form, right? The total energy in the universe does not change. Write that down. The first law of thermodynamics tells us that energy cannot be created nor destroyed. It can only be transferred or converted. Jot that down. Okay. The second law of thermodynamics tells us that when energy is converted from one form to another, some energy is converted to heat that is released into the environment. All right. So again, we saw that in our energy pyramid. As energy was being transferred from one trophic level to the next, there was an expenditure or a release of energy in the form of heat into the surrounding, okay? And so what we do understand from the second law of thermodynamics is that the energy that is available to do work decreases over time, okay? So we're talking about that potential energy, the event energy that's available to do work, can decrease over time. All right. So this is our visual here. First law of thermodynamics tells us that there's a transformation of energy. Like there's no energy created nor destroyed, but it can be transformed, rearranged, or converted into a different form. So if we look at this balance here, the same amount of energy that we started with is going to be the same amount of energy that we end up with, though it may look a little different. Okay. The first law of thermodynamics tells us that energy transformation occurs, but there is no net gain or loss of energy in the universe, in this system, within this system. Okay. So the second law of thermodynamics tells us that the energy can be converted to a different form. All right. So we can have free energy. We can have energy that's transferred to usable energy. Right. But there is no net gain or loss of energy. Okay. So again, these schematics show us that the same amount of energy that we start with is going to be the same amount of energy that we end up with, but that there may be transformations where different forms of energy is now available. So we have what we call potential energy or usable energy, and then energy that's unusable. Okay. So metabolism. We've talked about metabolism a little bit already. Metabolism is defined as the sum of the chemical reactions that take place in an organism. Okay, we're clear that these chemical reactions enables an organism to carry out activities that are required for life. All right, going back to our very, very first discussion of how do you know that you are alive? All right, there are a set of characteristics that an organism exhibits in order to be considered alive, right? Growth, maintenance, repair, reproduction, responding to stimuli, and everything that's going on around you requires this metabolism, okay? A energy expenditure. Okay, so we talked about this already, the types of metabolism, right? We have anabolism, write this down, requires energy. This is chemical reactions in which molecules are synthesized or new molecules are being created from smaller molecules, right? So for example, those proteins that are made from our amino acid monomers, right? That is an example of anabolism. Okay, this synthesis or formation of these new complex molecules from our smaller molecules requires energy. Anabolic reactions, anabolism, are chemical reactions in which molecules are synthesized or formed from smaller substances. All right. In contrast, catabolism, right? Catabolic reactions are those chemical reactions where larger molecules are broken down into smaller molecules. All right. So for example, the degradation of those large complex starch molecules into our monosaccharides, right? Which are our monomers. Okay. Catabolic reactions release energy. Right. That's what we see in cellular respiration, a release of energy. That is an example of catabolism. Right. So I would like for you to be able to identify and describe these types of metabolism, right? Anabolism and catabolism. One requires energy and the other releases energy. What questions do we have about this? All right. So free energy. Now we're talking about the ability to do work. We said that energy is the capacity to do work. So the amount of energy that is available to do work, right? Which is this energy, this free energy is required to carry out activities in the cell. Okay, so chemical reactions involve changes in free energy. Okay, so we can sort of predict whether or not a chemical reaction will release energy or require an input of energy, depending on what's going to happen in that chemical reaction. That's why those definitions are important. We have those anabolic reactions and catabolic reactions. We can predict whether or not we're going to require energy for this or if energy will be released. Okay. So free energy, this is the amount of energy that is available to do work. And this is required for cellular activity. All right. So let's look at this idea of a gain or loss of free energy. So remember, the total amount, the net amount of energy isn't changing, but the amount of energy that's available to do work can change. Okay. So if a reaction is going to release energy or require energy, there's going to be exergonic reactions that release energy. Okay. There's a net loss of free energy in the product. All right. So endergonic reactions increase in energy. There's a net gain of free energy. All right. Exergonic reactions will release energy. All right. So let's stop right here. I want you to work on these questions for the rest of class and for homework. All right.
Could you go back real quick? I was writing down the last part.
All right. So we're saying here that there are changes in the amount of free energy. All right. Exergonic reactions are going to release energy into the surroundings. So remember, we showed you that schematic where we had a system and then we had the surrounding, and then there was a barrier that was going to regulate the exchange of energy between the environment and the surroundings. So exergonic reactions are going to release energy into the surroundings. Okay. However, in endergonic reactions, energy is taken up or absorbed, all right, from the surroundings, okay? And so I wanted us to stop here conceptually and work on these questions today. I'm going to give you the rest of the class period to work on these questions. There are 5. Oops. There are 4 questions here. The first one is for you to define energy. You can work on this right now. We have a little bit of time remaining. Define energy. Write the questions down. Number 2, describe the first and second law of thermodynamics, okay, for your understanding. Number 3, why is free energy so important to the cell? Okay. And then lastly, distinguish between exergonic and endergonic reactions. Write these questions down. And I'm going to tell you which chapter. Let me tell you